All right, greetings everybody. Thanks for logging into our webinar. The title of this webinar is going to be Prospect Identification and De-risking using Cognitive Interpretation. This is an example from the Sergipe-Alagoas Basin in offshore Brazil. My name is Andrew Pomeroy. I'm a geoscientist here in the Houston office. Before I get started, just a couple brief notes. First, please mute your microphones. This is recorded and we do get feedback sometimes. And the other thing is, if you do have questions, feel free to type those in at any time to the text box using your GoToMeeting app. We want to thank PGS for their collaboration and the data that they've let us use and show to you guys. The cognitive workflow at the heart of GeoTeric is centered around reveal, interpret, validate. And this is applied throughout, enabling users to understand the geology through attribute analysis, to interpret what they see in the color blends rapidly and efficiently, and now to validate that interpretation. So in this presentation, we are kind of in the reveal and interpret part of the cognitive workflow. Just a brief outline for the presentation today. We're going to go over the data, show you what we had to work with. I'll give a brief geological context for the Seal Basin, and then I'll go into the workflow itself, where we use GeoTeric's full suite of attributes, including frequency decomposition and AVO blends. And we use these to reveal elements of the petroleum system. We can then take that into a CRS classification. We can do that volumetrically. And then I'll go into some of the conclusions and suggestions for further work. Onto the data itself. Again, we are in the Sergipe-Alagoas Basin, also known as the Seal Basin. This is in offshore Brazil. The data set that we're working with, coming to us from PGS, is a GeoStreamer multi-client data set. It's called the BM Seal 10/11. This is a pre-stack depth migration data set, about 4,500 square kilometers worth of data that was shot in 2014. We are lucky enough to not only have a full stack, but a near, mid, far, and ultra far stack that we can use to do some AVO analysis. We're also given one well. This is the Barra oil discovery well, a discovery made by Petrobras in 2010. We know about additional discoveries nearby. We don't know much about them. Those are shown here in this kind of cartoony image over here. This is the Barra discovery, and that is the Barra well shown along with the survey outline. Several other wells drilled within this basin, and those have made other discoveries, including this Cumbe shown here, the Farfan accumulation, Miriu, Moita Bonita, and Poco Verde. We really don't know too much about those, but we'll try and point those out as we go along. Just touching on the regional geology. Again, this is in eastern Brazil. The basin extends both onshore and offshore. It was created during the Jurassic and Cretaceous, during the breakup of Gondwanaland, where the South American plate was separated from the African plate. The classic sequences that we're looking at in this basin, starting at the base of the Cretaceous, start with deltaic silicic clastics, fluvio-deltaic silicic clastics, and then going into marine transgression, where we get more deep water deposits that we'll be focusing on for this talk. This is kind of a busy slide showing the overview of the workflow that was taken in this project. We first went into data conditioning. I'm not going to show you any of that today, but that has been done on our input data. And then the rest of the workflow is focused on using GeoTeric's cognitive interpretation tools to reveal elements of our petroleum system. So we use stratigraphic reconnaissance. This includes frequency decomposition, isoproportional slicing, to help us reveal elements of the source, reservoir, and seal. And then we go into structural reconnaissance, which helps us reveal elements of the trap, and in this case, elements of the migration story. We can then use those subangle stacks to compute AVO attributes, as well as uniquely in GeoTeric to create an AVO blend. And then when we put this all together, we can bring this into our interactive facies classification tool. This leverages machine learning, and it allows us to classify, in this case, using a CRS or composite risk segment type methodology. When we do all this, and we're able to combine these attributes and geobodies, we then can reveal risk rank prospects that can then go into further analyses, volumetrics, more detailed mapping, and so on and so forth. So starting with the stratigraphic reconnaissance, this is an image showing a uniform constant Q frequency decomposition color blend. In the background here, in the inline slice that we're showing, we notice several features popping out. Of course, this is the seabed up here. We also see several of these rafted fault blocks sitting along a what we can assume to be a shale detachment surface. This bright response here in the blend is actually an igneous intrusion. There are several of these throughout the basin, so those are good to be able to identify because they are significant drilling hazards. Then in the blend that we have mapped onto a horizon here, we see the Barra Reservoir here. This is a light oil discovery along with the well. We see that that sits on this kind of larger depositional system shown here with these nice channels popping out. And over in the foreground, we also notice a salt diapir, which are also prevalent throughout the basin. Bringing this into now an analysis to try and bring out the different petroleum systems elements, we can then look at trying to identify the source rock. In this case, if we can assume we know about where it should be stratigraphically, and we assume that the shale source rock is going to be represented in the color blend by a low frequency kind of dark red response, we can then take that into our IFC tool and highlight that, which is what I've done here. And we can create an actual volume out of that so that we can then use this to prove up to ourselves that we do have a regionally extensive source rock. We can then go into the isoproportional slicing tool, where in this case we're revealing not only elements about the reservoir, but also the trap, as many of these reservoirs, the known reservoirs, are stratigraphically trapped in this basin. So in this case, what we've done is we've used our adaptive horizons. We've interpreted a top Campanian, a middle Campanian, and a top Turonian horizon. And in the isoproportional slicing tool, we've then used that to create several more stratigraphically conformant horizons that we can then use to slice through the volume in a stratigraphically conformant manner, and we can map any of our computed attributes onto those. In this case, we're showing on this top Turonian horizon an envelope attribute, and on this one we've got our frequency decomposition. So this allows for rapid visualization and stratigraphic understanding. Then moving on into the structural reconnaissance phase, we can use our fault expression tool to create a CMY blend where we've combined our dip, structurally oriented semblance, and tensor volumes into this blend. In this case, in this deeper time slice, we're looking at some basement-involved faulting that we've revealed here. And then if we scroll up in the time slice, we then are able to reveal some post-rift faulting that we can then go ahead and interpret and start to build into the migration story. We can continue on the migration kind of story by computing a diapir attribute. This highlights Chaotic low amplitude zones, which can be used as proxies for hydrocarbon migration pathways. In this case, we see several potential vertical migration pathways, as well as potential carrier beds, shown here by these white dashed lines, and also potential regional seal where we get very low response. We can then co-visualize that with a fault density attribute. This highlights zones of high faulting. And where these areas are juxtaposed, we can then create an opacity blend that shows us areas where we can then start looking in more detail to build up that migration story, bringing the hydrocarbons from the source rock up into our shallower reservoir sands. We can then use the sub-angle stacks to create gradient and intercept volumes that we can then compute different AVO attributes from. In this case, we've computed an AVO product on the left. This can be good for highlighting class 3 sands. This is the Barra Reservoir in here. We can also compute a reflection coefficient difference, or a approximation of a reflection coefficient difference volume, which is shown on the right. This can help highlight all types, class 1, 2, and 3. When we look at the data itself, what we're mapping here is the well logs, as well as the full, near, mid, far, and ultra far substacks mapped onto the Barra discovery well. When we take a look at the data, we notice that most of the brightening, this is a class 3 sand, most of the brightening is actually on the ultra far stack. Now this presents a problem using the AVO attributes to do some prospecting within the basin, because when we calculate the gradient intercept, we're using Shui's 2-term approximation to do that, which is limited to about 30 degrees. You can see that our ultra-far stacks are in the range of about 30 to 42 degrees. So in GeoTeric, what we can do is use an AVO blend, which is not limited by any approximation of the Zopert's equations, and that is shown here. So what I've done is I have computed magnitude volumes for the near, far, and ultra-far stacks. I've then blended those together, and what we see is that areas that are popping out as being bright are areas that are having an AVO response. This is showing in here the Barra Reservoir with the well, and you see several other areas that are interesting looking as well. We can then apply our CRS approach now that we've got some knowledge about our different petroleum systems elements. We can combine those. In this case, in many cases in the industry, we use just map-based techniques to do this, where we combine, we classify these petroleum system elements based on our relative uncertainty or a risk of finding them if we were to drill a well, and then we combine those into a composite common risk segment map. In GeoTeric, we'll use the IFC tool to do this using our AVO volume, which can show us not only potential for reservoir presence, but also for petroleum charge. So if I take the Barra horizon, which is shown here, I've got the constant Q color blend draped on it. This is the well location. I can then drape the the near far ultra far RGB color blend on that. And then when I take this into the IFC tool and perform a CRS style classification where I'm mapping a high, moderate to low, low confidence zone, as well as the igneous intrusives, which you'll see on the next slide, this is what I get. So we see that the Barra Reservoir comes out very nice with this lobe shown here. On the other side, we get more yellows and reds. Since we're doing this volumetrically, I can then take this and drape it on my IPS horizons, which I'll show here. This is a little movie where I'll start going from shallow into the deep. The white polygons are demarcating our igneous intrusions. Those are shown in the volume in blue. So I'll just go ahead and start that movie. So we're moving down in the section from shallow to deep. You see a lot of those blues, and now that we go a little bit deeper, we're seeing some greens popping out. There's the Barra Reservoir that we just went through. And then we'll also see some of the other known discoveries. This is the Muriu accumulation, the Farfan Reservoir, the Moita Bonita and Verde as well. And again, as we continue to scroll down, we see several other greens and yellows popping out that, as far as we know, are not known discoveries. This is just another look at that. These are all of the surfaces shown at once. Again, we see a lot of nice depositional trends here, as well as these blue igneous intrusions popping out. If we then bring this all together, again, what we did was we started with our data condition reflectivity volume. We then computed our frequency decomposition uniform constant Q color blend. This helped us reveal elements of the petroleum system, such as the source, which is shown here. And the reservoirs, we were also able to pull out elements of the structural story, which helped us build up a migration by draping the fault diapir with the fault density attribute. We then brought in the AVO color blend, which helped us reveal the reservoir as well as a potential for reservoir charge. When we then bring that into the IFC tool, we leverage machine learning, and this helps us classify the entire volume based on that Barra reservoir. And we use our IPS slices to scroll through that entire volume so we can visually look at those potential prospects. And then we can use body labeling to actually extract those potential prospects. So what you see here, anything that has the purple polygon is a known discovery, and anything that does not is a potential prospect that can be taken into further analysis. It is ready to put into our volumetric calculation tool and any other further analysis that would be needed. That's not quite the end of the story, though. You may have noticed that our CRS volume was really only highlighting class 2 or 3 reservoirs. We can also highlight a class 1 reservoir. So in this case, what I'm showing on the left is a channel that popped out. This is a deeper channel down near the source rock, which was identified excuse me, in our uniform constant Q blend. We notice in the middle panel that it actually maps as a low confidence area. This is because we actually classified seeking generally class 2 and 3 reservoirs. If you look at the AVO blend itself, you notice that a lot of these kind of amalgamated point bar type deposits actually pop out in a reddish or orangish type color. So that indicates that they are brighter on the nears. This is what a class 1 response would be. So the theory would be that we're at a depth now that the sands have compacted to a point where they're harder than the shales. So we would expect a brighter response on the nears than on the fars. So what we can do is just take that back into our IFC tool. We pick a representative sand as well as a representative shale, and we reclassify, in this case, just using a higher confidence versus lower confidence classification, and this is the result that we get. We can also prove that up further by taking this into our cross-plotting tool, where in this case I've used the gradient and intercept volume that we computed for our AVO attributes to map the representative shale, which you see pops out on the shale trend here, and then the sand that I picked actually pops out in the AVO class 1 region of the plot. So just to wrap up, again, this high quality, broad bandwidth, long offset data set proved to be very well suited for attribute calculation reconnaissance in GeoTeric. When we combine these attributes, this includes the AVO blending, our adaptive interpretation tools, geobody segmentation, and just the use of a single well. This led to rapid generation of several potential prospects. The AVO blend was found to be very useful to highlight these known discoveries as well as several other potential prospects. And it can be calibrated for AVOs class 2 and 3 as well as class 1. When we combine and co-visualize these attributes that reveal elements of the petroleum system, this allows us to use a CRS-style approach or a CCRS-style approach, which leads to reduced risk on revealed prospects. Now again, I mentioned that we could then pull in our geobodies into volumetrics and do more detailed mapping within GeoTeric. Another thing that we could do is pull it into Validate to use some actual rock properties modeling to model not only the reflectivity response, but also the response in the frequency decomposition color blends. So with that, I'll wrap up. Again, thank you to PGS, and I'll ask if there's any questions.